Hi guys, today I want to share two more expert level problems with you. This time they are interactive, so also a bit different from the usual setup, I guess. So first we'll take a look at the problem from a LA token, a late token. I'm not exactly sure what it's supposed to be, but yeah, apparently it has to do something with some cryptocurrency or something like that. So this problem is from div1 plus div2 round. It's problem D, and it's 1800 rated. It's a cute problem mathematically. I really enjoyed solving it, although I solved it reasonably quickly, but still, that's a nice problem. In this problem we have a tree, or rather we don't have a tree, but let's say I created a tree, but I don't tell you what this tree is. So I just tell you that, well, you know what, it has like 5 vertices or something like that, n vertices, right? Now with that information in mind, you can ask n over 2 rounded up queries of the following form. You pick an arbitrary node in this tree. You call it R because it's going to be a root of something. And what I tell you is I tell you the distances from this root to all other vertices. For example, I can say that this one is 1, 1, 2, 3. And your task is to restore the tree in at most n over 2 rounded up queries. Approximately half, but maybe a little bit more if n is odd. So feel free to pause the video and think for a moment about this problem if you want to. Assuming that you already did that, I'll start going through my observations on this problem. So first I thought like, well, if I know the distance is 1, then this edge surely belongs to the tree. So I thought like, okay, so... And then I probably could carry out some analysis on the rest of the vertices, but I really didn't want to do that, because like here it's unclear whether this is an edge connecting the two vertices to R, or this is the edge. In general, if you were to ask about, let's say this vertex, call it root, I tell you know what, the distance to this vertices is 1, and the distance to these two vertices is 2. You have no idea how, like you are fairly confident that these edges are in the tree. Then you have no idea whether this is connected like this, like that. How about this other vertex? You don't know, you just don't know. You get a what's called layered structure, layered BFS structure. And you don't have an idea of what are the edges here, or imagining that we had more layers, what are the edges between layer 2 and layer 3. So that's a little bit unsettling. But then I started thinking like, okay, so I probably don't want to carry out some specific analysis on like which edges go where, because that's going to be take a long time. So what I maybe want to do instead is focus on the neighborhood of my root vertex, because we already figured out that whenever we ask about some vertex, we get all edges adjacent to this vertex. And then I started thinking like, okay, so basically, I have like a lot of queries, so I don't need to do a lot of work per query. So what I could do instead is try to cover all edges with my vertices. That's just called a minimum vertex cover, I believe. It's the minimum subset of vertices, such that each edge has at least one of the endpoints in these vertices. And then I realized that, well, in general, minimum vertex cover is an NP complete problem, so probably can't do that in polynomial time. I mean, not probably, but no, actually, yeah, you probably can't do that in polynomial time. So instead, like the only class, there are special classes of graphs where you can do that. I believe that one of such cases is a bipartite graph, and then I realized that, well, wait a second, a tree is a bipartite graph. More specifically, like there is a very easy bipartite structure that you can see on this picture already. Like all even numbered layers, they form one part of the tree, and all odd numbered layers form the other part. And then I start thinking, well, okay, so like I know for a given that if I query all red vertices, then I will restore all edges, right? Because like each edge goes from a red vertex to a blue vertex. But it may be the case that there are way too many red vertices for me to query them all. Let's say something like this. I have 4 red vertices and I'm only allowed to make 3 queries. And I start thinking, well, okay, so I can't just query every even layer, but what about, let me be a little bit smarter, and whenever I see something like this, I say like, okay, you know what, I'm going to query whatever color has fewer vertices, because that just makes sense. Ignoring this vertex because we already queried it, so there is no need to query it again. So what we see here is that we have some number of red vertices, some number of blue vertices, and then we have a special vertex root, and such that their sum is equal to n. I said that I want to query whatever like minimum of red and blue vertices, like whichever color has less, has fewer vertices, I will query that. So what I'm saying is that, well, this is surely at most their sum over 2, right? This, and then rounded down because all numbers are integers. We have something like that. However, their sum, as we can derive from that equation, is equal to n minus 1 over 2. Then remember that we also queried this root vertex, so we actually have one more query. We asked that many queries. Now we can add like this 1 inside. What we'll get is something like this. And I say that this is, I believe, equal to n over 2 rounded up. Let's have a quick mental check. So if n is 2k, that is even, and this will be just k, and this will be 2k plus 1 over 2, so like k plus half, but then it gets rounded down, so still k. If n is equal to 2k plus 1, that is, it's odd, and this one will be k plus half, but rounded up, so k plus 1, and this will be 2k plus 2 over 2, so that's k plus 1, rounded down, still k plus 1. This is just equal to the number of queries that we are allowed to make. That is, of course, like this is an upper bound here, so we don't always use all our queries. In case we picked a reason like a lucky root, such that the number of, let's say, red vertices is much smaller than the number of blue vertices. But in general, that was a really nice problem. It tested your understanding of concepts like layered BFS structure and also basic knowledge about trees, that a tree is a bipartite graph. So you can, like, if you want to each edge, then you probably can get approximately a half of the vertices, and you need to be a little bit careful about, like, how to do it exactly. So very nice problem mathematically. I have not seen this trick with layered structure for quite some time, since some math competitions I participated in, so really enjoyed it. Not a very difficult one, but maybe the fact that it's interactive added a little bit to the complexity. Let's take a quick look at the implementation section as we usually do. It takes quite some time, I'm assuming, because we have a lot of input-output going on, like a quadratic complexity, of course, because we make of n queries, and each query, the answer to the query, takes all of n memory. So the way I usually, since a certain point in time, I solve interactive problems by defining functions like, say, ask and say. So ask will ask a query, do all cout, flashing, stuff like that for me. Potentially do some, like, early exiting if I need that, like crash eProgram if I fail to answer some queries, something like that. It's really convenient to have it in the wrapper function. And I have a function say that prints the answer, more or less. Again, does all cout flashing that we need to do. So in this particular problem, funnily enough, these functions take most of the space, because then what we do is we, like, query a depth, like pick an arbitrary root. Let's say a root is equal to 0. It's also convenient that these guys can take care of, like, adding +1 for you, so that in your main program you can use your normal 0-based indexing. So I pick arbitrary root, I query what is the depth in this BFS layered structure, and then I partition vertices into even depths and odd depths. I pick whichever is smaller by this nice trick. I ask about all vertices in this thing, and I print edges. You may have noticed that I did nothing here because, once again, ask function is convenient because it can do things for you, not only reading input. For example, here, whenever I see a distance of 1, we already said that it means that this edge is an edge R3. So why don't we just add it to our list of edges right here? Like, we are not going to do any processing afterwards. This is, of course, not a very good modularization of the code, because, like, this function has an extra purpose of not only asking for input but also filling the set of edges. But who cares in competitive programming, right? If you can do it once here instead of doing it like both here and here, then why not? Like, it could have been a separate function that probably would have solved modularization problems, but we don't necessarily care about it here. That is just a very nice trick I learned from Maxim Horokhovsky. I imagine that is how you pronounce his surname in English. So a very well known in certain communities, legendary grandmaster. I was looking through his submissions and I saw this trick and I thought, like, oh yeah, that is what I wanted. So yeah, not that. Let's take a look at the second problem that comes from very recent Delta's summer round. Problem D, take a guess. So we have a hidden array. We can make two AND queries of the following form. We can either query bitwise AND or bitwise OR of two numbers. That's all we can do. And we need to, for some reason, it's funnily worded. We need to find the case smallest number. I thought that there is no reasonable chance that we can find case smallest number without restoring the entire array. So luckily for me, I went straight away to restoring the entire array instead of spending too much time on thinking how the hell do we get a case element without getting the array. That helped because it turns out that we actually can restore the entire array. And this is again a cute problem that uses the following tricks. So like if you have numbers x and y, and you can say a lot about them from the values of x and y and the values of x or y, bitwise of course. The reason why this works is the following. Let's have a truth table that you probably have not seen since your university years. So we have like these quantities. Now there are 4 options for the pair of bits in x and y. Let's say x and y are booleans for now, so they only have 1 bit. Often in such bit problems we can process bits more or less independently, so that this is not going to change anything. So if both of these are 0, then both of these are 0 as well. If one of them is 0 and the other one is 1, and this body is still 0, but this one is already 1. If both of them are 1, then both of these are 1 as well. So the trick is like we can figure out how many bits x and y have set in total, looking at this output. The only inconvenience is if they have exactly 1 bit set in common in total, you don't know which of x and y has this bit. That's a little bit not very nice, but still. Another way to put it is that sometimes people say that we know the sum of x plus y because that is the same as the sum of x and y plus and x or y, bitwise of course. That is a nice equation that I did not use it explicitly, but you can get a little bit simpler solution in terms of implementation that's than the one that we are going to arrive at given this kind of reasoning. And I started to think, okay, so I can spend 2 queries to more or less determine 2 numbers. Can I do something better? Like, let's say it tells me more or less like which one has a bit set of. What happens if I ask about pairs A1, A2, A2, A3, that is not 3, A3, A4, etc. all the way up to an minus 1, an, and also loop back to ask about an, a1. That will tell me a lot of information, but here I got a little bit stuck, like if n is even, then this approach appears to be bad. Like you can't actually restore the numbers given if you ask such queries. You already wasted all of your queries, so maybe that is not the way to go. However, I noticed that if n is if n is odd, then we can restore numbers in such a scenario. But I really didn't want to distinguish them, so I thought like, okay, maybe we can just pick our n ourselves. Like what happens if I ask queries like a1, a2, both and or a2, a3, and then a3, a1. Once I queried all of those, I can I was thinking about this problem in terms of graphs. I have like my graph of numbers. If I have a cycle of odd lengths, then I can restore the numbers, and all I want is my graph to be connected. So basically, after this, I just connect one of such vertices to all other vertices, which means asking queries A1 AI for all I from 4 to n. It was my kind of reason behind this problem, because I was thinking that asking such two queries, it's sort of drawing an edge between x and y, because you get a lot of information about how they relate to each other. Specifically, like it will become more clear how we restore the numbers after asking such queries, after we take a look at the implementation. But imagine that we knew x, right? Imagine that we know x. And by asking such two queries, we can restore y uniquely, right? You just look at this like 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 1. They are all distinct, so they map uniquely to the values of y. That was my intention. Like after asking these three queries, I learned the value of all these vertices, in particular this one. So now after asking such queries, I will learn the value of this vertex. So our problem consists of two stages. First, we'll learn three numbers in a triangle. And second, using the fact that we already know one of them, numbers, we will pair this number with every other number and learn the value of the other number. Technically, there's also stage 3 at which we sort the array in output case element, but that's not really relevant to the problem itself. Now the only thing that remains is how do we restore the three values from 6 queries about them. And implementation probably answers it best. Like once again, we have our convenient wrappers. They take care of always print and finish and not something else. Let's say one benefit is that you can't make a typo here, because you will always see, well, you can make a typo, but you will always see the typo. It's not like you made a typo in one of like several if case else branches, and then you only the test number 69 caches it or something. No, like if you make a typo here, then you will always see it. That's one side benefit. We make all such queries and we restore numbers bit by bit. I said that I will characterize all circumstances under which A0, that is x, will have this bit set. I said that this happens when one of the following happens. Either x and y have this bit set, because if it does, then like both x and y have this bit set. Same with z and x. And I suppose, okay, imagine this does not happen and this does not happen. What if x has its bit set, right? But bitwise AND of such guys does not have bitwise AND set. Oh, I imagine that could have been simplified. Yeah, whatever. But actually, what I was thinking about, like if x has this bit set and bitwise AND of these two guys does not have this bit set, it means that they have exactly one bit turned on in common. And these guys as well. And then I was thinking like, okay, actually imagine that I don't know this fact. The only thing I know is that these guys have this bit set. That is what I check here and here. How do I check if X actually has this bit set? Because what I can have two options. Either these two guys together have two bits set, meaning that they both have this bit set, then X doesn't, or they have 0 bit set in common, meaning that they both don't have this bit set and X does. So I just realized that, well, we can query for the value of Y and Z in this bit and check if it's off, because if it's off, then the bit in X is on. And then I have two similar constructions here and here to restore the bits of Y and Z accordingly. After I did it, I just loop over all numbers, all remaining numbers. I make two queries, X with AI, X or AI, and I restore all the bits by several if-else statements. And I print, then I sort, and then I print. That is a nice kind of identity that you want to know if you want to solve certain higher rated problems. That if you know bitwise AND and bitwise OR, then you almost can restore the original two numbers, and you just need a little bit more information about them to actually restore them. That is a recurrent pattern in bit problems, I believe, around this difficulty. So let's say from 1800 to 2000, you're likely to face such problems. I remember at least one more interactive problem that required you to do something with bitwise operations on a hidden array. And probably there are more that are not necessarily interactive, but let's say they are just concerned with like bitwise AND and bitwise OR. So yeah, I wanted to share these two problems with you because I think they are sort of characterize the corresponding areas around this rating. So you are likely to see problems with similarish ideas in your practice, and that's why it's important to learn such ideas. That's kind of a message here. So once again, that's it for me for today. I hope you learned something new, and with that in mind, I'll see you tomorrow with more problems, but tomorrow we'll have master level problems. I decided to not be over specific in how we characterize problems, mainly because the specialist background doesn't really look good on thumbnails. So we'll have 3 categories. That's not 3, now it's 3. So expert, master, and then grandmaster. Probably there are one bit too much content about grandmaster level problems because I'm assuming that's a little bit difficult for some of our viewers, and you're mostly interested in expert and let's say master level content. So that's it. I'll have bluish, yellowish, and reddish. So kind of like Codeforces logo. Funnily enough, in Codeforces logo they have colors in the right order. The reddish is 3rd place, the yellowish is 2nd place, and bluish is the 1st place. But yeah. So yeah, that's it for me for today, and I'll see you tomorrow. Bye bye, guys.